need. Okay, so let's start. So this is the fourth class, right? Fourth class. So we are going to use the tools that we developed last time. So including essentially the greens function that I presented last time. Very briefly, we'll go deeper today, okay, and see how we can use that for a problem of scattering, okay. We use also the retarded potential that we discussed also last time, and we will explore some specific case, especially the case of particles which are small. So different type of scatterers. Okay, and just to start, before starting the course, I like to introduce some exhibits of some artists during the class. So each class I will present someone else or some work. Okay, this is an old work by Georges de la Tour. I don't know if you know this painter. He's a very famous French painter of the 17th century. Georges de la Tour. So he was a French painter, and the method that he used is called the chiaroscuro, which means that he plays on the light and the shades. Maybe we should turn off the light here. So there is a play between light, and it's really amazing because I like this painting because he really captured a lot of effect that we are discussing. Okay, so you can see here, you see the hand of the young girl here. If you zoom on, you can see what he really painted the scattered light to the skin. Okay, which is just remarkable here. And I found that very, very interesting, very nice. So most of his work is at the Museum of Le Louvre in Paris. Okay, so over the slide you'll see some other paintings from this famous painter, Georges de la Tour. Okay. So let me outline the course today. I will first give you the general formulation for the scattering of light using the green function. Okay, this is called the integral formulation. You see, it's a formula that is difficult to use. Okay, so we'll go into some approximation. So the first approximation we will consider is the case of weakly scattering scatterers. This is called the Born approximation. The second case will be the case of small scatterers compared to the wavelength. Okay, and I will detail here the calculation and how far we can go with in that specific case. And then we'll go to more or less the same class of scatterer. Relegance device scattering. This is in the case where the scatterer, they don't have a strong index contrast, so they are like weak scatterers. Okay, so the hypothesis is not on the size but on the index contrast. And then we'll go to the other limit, which is the case of very large scatterers, in the case of meteori. Okay, I will not go too much into details here, but just to cover all the cases that we know how to handle those problems. And I will show you a much more complicated case, which is the case of anisotropic scatterers. That means that they don't scatter the same way in different directions. Okay, so this will be mostly just examples and simulations that we have done in this topic. Okay, good. So let me first give you a small reminder about the green function. So you remember that the interest of the green function or the green tensor is that once it is known, then you can calculate the response of the medium to any source. Okay, so starting from a radiating source, okay, the green function tells you what is the electric field away from that source. So let's take the case, for instance, of a dipole. Okay, the dipole is at position r prime. It has a moment p. Okay, so the radiated field E of r at some distance r from the dipole is given by this formula. So mu0 omega square, G is the green tensor times the polarization, the dipole moment in that case. Okay. So that's the tensorial expression for the relation between E and P.
That's a scalar product between G and P.
G is like it's just like a matrix. It's a tensor, okay.
Like a matrix.
So it's a 3x3 matrix multiplied by the vector P, which has 3 coordinates.
Yeah.
Okay. So this is important. This is the field that is radiated by a dipole. Okay. So we saw that this is typical of an antenna, for instance, that radiates electromagnetic wave away from that point. Okay. Then, if you, instead of a point dipole, you consider a distribution of dipoles. Okay. So the radiated field or the scattered field, I put it like that here, at position r and frequency omega, by a given scatterer of any shape, okay, of volume v, with some polarization density p of r, okay, is given by, so you need to integrate the product G times P over the element volume. Okay, if you want, this is exactly the dipole moment for an element of volume d3r, and you sum over all the elementary dipoles, okay, over this volume. Okay, that's fine. So that's the definition. Just to remind you, so for a scalar field, the Green's function satisfies this equation. So the Green's function is the solution of the wave equation when you have a point source in the second number of the equation. That's interesting. If you look, you can look at it as so. This may be a little more formal, but so if instead of the scalar field you consider the electromagnetic field, which is a vectorial field, so E is a vector. So actually you need to apply this operator to the field to solve the equation, okay? And actually G, the Green tensor in that case, is the formal invert. You say invert, yes. The inverse of this quantity here, of this operator. That means that this operator times G is equal to the identity. Okay, so you can see that as the invert of the operator itself. So from a more formal point of view. Okay. So it maps a vector source P of r, okay, to a vector field E. So you have the scattered field is related to P by this formula, thanks to the Green's function, which is the invert of this operator here. So this looks like given. Maybe we can say more about that. Maybe we can try to demonstrate this formula here. Okay. So we see where it comes from. Okay. So let's say, as an exercise, let's show that we have indeed this relation between the scattered field and so it's a large P here, and the polarization density of the medium, of the volume of the scatterer. Okay, so how do we do? How do we proceed to show that? I give you the main steps. So you have to consider the space outside the scatterer and inside the scatterer. Okay, so outside the scatterer, you have the wave equation with a 0 on this side, so it's the homogeneous equation itself, okay, where E is the solution of this equation outside the scatterer. And inside the scattering volume, you have the same operator applied to E, except that you have now some index of refraction, if you want, okay, some epsilon here. So K2 is omega square root of epsilon 2 times mu 0. Okay. Right. So these two cases can be grouped in one formula, if you prefer. This can be rewritten as a single inhomogeneous equation, which includes both domains, outside and inside the scatterer. Okay, so you have the operator applied to E is equal to minus mu 0 omega squared P of R. Okay, where P of R is just epsilon 0 times epsilon minus 1 times E. Okay, so that's by definition the polarization. And E and epsilon can take two values. Either it's 1, in that case this term is 0, and we are back to this formula, okay? Or it is equal to epsilon 2 over epsilon 0, and that gives you a correction here to the k vector here. Okay? So it's a way to group actually the two cases in one formula. So we have a differential equation with the constant term, with the source term here. Okay. So to solve such an equation, the solution of this homogeneous equation is the sum of the solution of the homogeneous equation plus a particular solution of the inhomogeneous case. Okay. So that's the general way to solve such an equation. I'm sure you are familiar with that. Yes. So what is the solution of the homogeneous equation? So this part here describes the field in absence of scatterer. Okay. So this is simply the incident field. Okay. No scatterer. You have just the field incident field E incident as a function of R. Okay. And the second term describes the scattered field ES. Okay. ES of R generated by the source term P of R, with a particular condition that the field vanishes at long distance. Okay, so we have a solution which is actually the incident field plus the scattered field by the object, and then you can choose a specific case where you have a vanishing field at infinity. Okay, so now we can introduce the green function, the free space green function, which is defined, as we said before, as the solution of the wave equation with the source term at position r prime. Okay. So you can take into account that we have this equality here. It took me hours to find out where this was coming from. I mean, because it looks so simplified. I mean, so simplistic. Actually, this is very simple. It's because here this operator operates on R. It doesn't operate on R prime. Okay. So it took me time to find that. So actually, you can take the P out of the product, and this gives you the operator which applies only on G. Okay, and not on P. So if you use that, you can introduce P, you can multiply this expression by P everywhere. So we get here, so you have here this term here, which comes inside because of this equality. minus k0 omega g p is equal to p times delta. So I just multiply by p everywhere. And then you can integrate over space, and you get so delta. So integrate over space. What did I do here? Yes. Is that logical for you? Yeah, just let it like that. I mean,
K0 become to K1, huh?
So no, yeah, that's a mistake of the K1. I meant K0. Okay, that's what I was confused. So this is K0. Okay, there is no K1 here. So it's an older notation that I was using before. Okay. So here I'm just reproducing here by integrating over the space. Okay, over all dipole moment here, which introduce P. Okay. So by analogy with the initial equation, the starting equation here for E, you obtain that E. So here E, the scattered part of the field is exactly the term in the integrating term here. Yes, this is just the solution. Actually, E is the solution of this equation directly. Okay. So this is what I wrote in the previous slide. Is that clear? So this term plus, so this is the particular solution for inside the volume of the scatterer, plus the incident way gives you the total field scattered by the object. Okay. So that gives you the expression that I dropped at the beginning of this session.
I didn't understand the difference between ER and ESR.
ER, yeah,
the field E and the field ES.
Right. This equation was including both the outside the scatterer, inside the scatterer. Okay. This actually is true. This is true actually inside the scatterer when you integrate over all P here. Okay. So this term is the particular solution. This is the case of the inhomogeneous equation. Okay, which is due to the fact that you have charges inside the volume of the scatterer. Okay. This term gives you this relation here. So for the particular solution of the inhomogeneous equation, this is scattered, okay, and this is exactly this term here. Okay, so if I show you the previous slide. Okay, so we said that actually this equation, okay, is as a solution which is the sum of the incident field plus the scattered field, which is the particular solution of the equation. Okay. So that's how I get to this expression here. Okay, so that will be useful to understand what's coming next. Okay, in the same spirit of solving the equation. Is that okay? Any question? So it's good to see where it comes from, just not just formulas. Okay, so let's define the full formulation of the problem. Okay, which is called the integral formulation. So the relation that we are going to develop here reflect that the fact that each volume of the scatterer behaves like a source, like a dipole that emits, that radiates a field, okay, with some dipole moment P, okay, and at some distance, actually, the field is a superposition of all the field radiated by all these elements, okay. So let's see. So we start from so we want to get the field at some position R, okay? So we said that this is actually composed of the incident field and the scattered field, okay? Superposition principle, okay? So if you replace ES as we formulated it before, so we have this expression here. So if you assume that around the scatterer we are in free space, okay, so instead of the general green function here, you can use the free space green function, which is the green function in the far field, okay. So that's the equation for the field at some distance from the scatterer, okay, which is the sum of the incident field plus the contribution due to the radiation of the group and the volume of scattering in this region V, okay. So incident field plus scattered field, which is the immediate field by the object, by the scatterer, okay. So this is not an explicit formula, okay. So it's quite difficult to solve. We know that in the far field we expect to have a spherical wave, okay, away from the dipole source, corrected by a phase term. So that's what we have if we write G0. Okay, so G0, the free space green function. You remember this expression from last week. So it's a spherical wave, okay, plus a correction here due to what's going on inside the scatterer. Okay, so there is a phase term that will correct, that will be added to the spherical wave.
What is U?
U, you remember, U is the direction from let's say the center of the scatterer to the position where you want to measure the field.
It's the
Sorry, U is the unit vector. Yeah, U is the unit. Yeah, and you remember this actually tells you that the field is orthogonal to that direction, U, okay, which is true in the far field. We expect to have the E field and the B field orthogonal to the K vector, okay.
It's the direction of the propagation of the wave.
Right. Okay, the K vector, right. U for U,
Yeah.
right? And this term is orthogonal actually to U.
So U times U is just 1.
Sorry.
U times U is just 1.
It's a notation here. Actually, it's kind of it's a tensor notation. It's not just U what. Okay. Actually, what you have is that if you apply this UU to P, for instance, then you get U times PU.
Yeah.
That we used that last time.
Yeah.
Okay. Okay. So there is a way to reformulate this integral equation by writing that the polarization is given by this expression. So what is epsilon? So the scatter is described macroscopically by its dielectric constant epsilon, okay, or the index of refraction, which is the square root of epsilon. Okay, and you can write that P is equal to epsilon 0 times epsilon minus 1 times the field. So inside the scatterer, okay, R prime is inside the scatterer, okay. So this is a well-known relation of the polarization related to E, okay. So if you just replace that inside the equation, so that is just replaced here, okay. So now you have the field away from the scatterer is related to the incident field and the field inside the scatterer, okay. And all the problem is to calculate this field here, okay. The problem is to know what is the field inside the scatterer, okay. all what we have done in the previous courses was to be always in the far field, so we ignored what was going on inside the particle. Okay. So this is the unknown. In general, this is the unknown. We'll try to calculate that. The first step, obviously, is to say that the field inside the scatterer is simply the incident field. Okay, that would be like the first order approximation. Okay, to say that the scatterer is just traversed by the incident field. Okay, so that's the case of weakly scatterings, weak scatterers. Actually, it's called the Born approximation. That we will see that next, and we'll be able also to solve the problem for small scatterers and also for spherical scatterers. That's the main cases where we have a direct solution of this integral equation. Okay.
It's missing epsilon 0 on this equation, no?
Yes.
It's missing, I think.
Yeah,
epsilon
epsilon
0.
0.
And the other?
Here? Yes. It's okay.
Okay.
Where do you want to put it?
No, it's fine.
Okay. So
I thought it needed to be like epsilon 0 also on the other expression.
where?
No worries.
Okay. So just the notation is not the same as the changing, but it's epsilon 0. Okay. So that's the dielectric constant.
נכון, אבל אני מפעיל את זה כאן. אז מינוס 1 כפול epsilon.
Okay, so this is a very important formula, and that tells you how so you have a field incident inside the scatterer. Okay, this field polarizes the scatterer. Okay, so that's what happened here. This polarization is due to the incident field that create a polarization in the medium. Okay, and this polarization will after that radiate back the field in all directions. That's the scattered field. Okay, so the process is always like that. You have an incident field, the field polarizes the medium, and this polarization radiates energy away from the scatterer. Okay, so incident field, the field. The question is this field here inside the scatterer the same as the incident field? In principle, no, because you have a complex object. Okay, so this incident field will just meet different atoms, molecules. I don't know. I mean, there will be a lot of interaction there. So the field inside can be quite complex. Okay, but this is the field which result in the polarization of the medium. Okay.
So we have two parts, the part of the field inside the scattering medium and the field outside.
Right, so actually the field outside is here, okay?
But it's incident?
So this field outside is the result of the sum of the incident wave, which is just the plane wave that comes, okay?
And the scatter.
Plus
and the
this
scatter,
this component is the scattered part, okay? But the scattering is due to the field of the polarization inside the medium, inside the scattering volume. Okay. I mean, you have all the physics is captured here in this equation, but you cannot do much with this equation. Okay. Okay, so we'll try to go over these simplest cases. So let's talk about the weakly scattering. You see the piece of paper? That's very nice. I mean, you see it's like it diffuses actually the light from the back. Okay, so let's deal first with weakly scattering scatterer. What does it mean? A weakly scattering object is an object for which this term actually is very small. Okay, so if you want, the index of refraction is very close to 1. Okay, so the medium is almost transparent. It's called translucid. Okay, translucid medium will be weakly scattering. So the incident field is weakly perturbed by the object. Okay, the system, if the system is diffuse, you don't take a dense system. We are in the regime of single scattering. Okay, and in that case, you can use what is called the Born approximation, which is really the first order approximation of the integral equation. So this is here. Okay, so you just replace the field inside by the incident field at position upright. Okay, so that simplifies the problem. The field within the scatterer can be approximated by the incident field, so the integral becomes explicit, and you can calculate it. Okay. The second case that I want to consider is the case of small scatterers. We will see next in the next sessions. We see that starting from this approximation, actually you can describe multiple scattering. Okay, you can say I'm scattered once by a weak scatterer, then a second time by a weak scatterer, and you can actually iterate the process and use this equation actually to describe the multiple scattering of light in that particular case in the Born approximation. So this is just like the first order, and then you can go beyond that and go through the full expansion. Okay. I just want to see. Right, okay. So let's consider scatterers now that are small compared to the wavelength. Okay, so what does it mean? I just want you to warn you on this point. Okay, so R here is the size. Let's say R is the size of the object. Let's say it's a sphere, for instance. So R will be like the radius. Okay, so it's not only this condition that R should be smaller than lambda, but it's also that R should be smaller than lambda over 2 pi m, where m is the ratio between the index inside and the index outside. Okay, why? Because it tells you actually that the wavelength.
The index of the wave that is coming back, like the scattered one.
No. You have a medium, which the scatterer itself. Okay, this is like a medium with some index of refraction, or some epsilon, right?
Okay.
Okay. This index of refraction changes the wavelength of light. Okay, the wavelength actually in a medium with some index of refraction larger than 1 will be smaller than the wavelength in the free space, right?
Yes, of course.
So if you want to compare the size of the object with the wavelength, you should take the wavelength, the actual wavelength, the wavelength inside the medium. That's the point.
Yes, I wanted to ask about the M.
Yes. So what is important is the ratio, actually, not only N1, but the ratio between the index of refraction inside the scatterer and outside. Okay?
Okay.
Because if you put like, let's say, I don't know, a bit of glass, okay, but inside water, the contrast will be small, okay.
So N1 is the one inside.
Right, and N0 is outside, okay. Yes. But in general, N0 is 1, okay, and here you have to consider lambda over N1, okay, which is smaller than lambda itself, okay. So be careful with that. The condition is not always fulfilled, especially when you have a very high index medium. The wavelength becomes very small, and then you cannot neglect the size of the object compared to that wavelength. That's what I wanted to say. Okay. So the small scatterer can be considered as it was placed in a uniform electric field incident. Okay. The scatterer own field caused by the electric polarization modifies the field both inside and near the scatterer. Okay, the field scattered by the object, okay, causes the electric polarization. Sorry. So the field caused by the electric polarization will modify the field inside and outside the scatterer. the next condition here, which is important, is that the scatterer, okay, it is small, but it is also considered as homogeneous, okay. That means it has a uniform dielectric constant, epsilon, okay, which means that the field within the scatterer is uniform. So we don't know what is the field, but at least it is constant, okay, because it's a homogeneous medium with some fixed dielectric constant. So if you know that, then we'll see actually what the approximation that we can do in that case. Okay, we'll go through that. So based on this approximation, I just want to review with you a very simple case, which is the electrostatic case. If you remember, if you consider. Okay, so we'll come to that. But first, I want to review with you the case of the electrostatic dipole. You remember? So you have two charges, plus and minus, and you want to know the field at some distance far from the dipole itself. Okay. So here the dipole is not oscillating. It's oscillating. Okay. There is a polarization, but the polarization does not depend on time. Okay. So this is electrostatic. That's the case of electrostatic. So let's consider a dipole with two charges, minus q at point A and plus q at point B, separated by distance L. We observe at the point M, okay, there is an angle gamma here, the distance r from 0 to M, okay, and the dipole moment is given by q times the vector AB. Okay, so AB is as length L. So the question is to derive the static electric field in the far field. Okay. So you remember how to do that? Yes. So you start. What do we start with? We start with the potential. Okay. The potential is a scalar quantity, so it's quite easy to handle. Okay, so we know that the potential created at some point by a dipole is given by a charge, not by a dipole here, by a charge. V is given by 1/4 pi epsilon 0 q over r. Okay, and so V, the total potential at that point M, will be the sum of the potential given by A and the potential given by B. Okay, so there is a superposition of the two potentials, which are given here, and there is a little bit of math here to calculate 1 over Bm minus 1 over Am. So you can calculate Bm and Am. Bm square is given by the general formula. This is the Pythagorean formula, but generalized actually for any triangle. Okay. If you remember this expression, yes.
Cosine.
What do you call that?
Cosine.
Yeah. Right. Okay, so that gives you OM square is as R square. OB is L over 2 squared minus RL cosine gamma. Gamma is this angle here. Okay, so you have the expression for Bm, you have the expression also for Am, same calculation, but you have a plus here. The sign changes here. So when you calculate this expression, 1 over Bm minus 1 over Am, that's what you get to the first order. So you take the expansion, because it's 1 over, okay, so we take the expansion. So 1 plus minus 1 minus, and you are left with this term actually twice. So you have Q L cosine gamma over this expression. Okay, this is precisely the dipole moment times R. Okay, the direction of OM over 4 pi epsilon 0 R to the power 3. Okay, we have power 3 here. Now, if you want to get the field, so we know that in the static case, E is given by the gradient of v minus the gradient of v. So you can calculate that in the polar coordinates r and gamma. I pass the calculation here. And at the end, you can group, actually, if you can leave it like that, or you can group actually the two into this expression here, okay, which gives you the E field at position R. Again, you see here this UU minus I, okay, which tells you that actually the field is perpendicular to R, okay. So that would be like the line, the field lines, okay. So at any position, the field would be should be perpendicular. Not very clear.
The last formula is from taking these two and combine them?
Yes, yes. Okay, so actually the only direction for E is the direction orthogonal to R, okay, given by this term. Yeah. Okay.
So the field is equal for every R. For every,
right.
Yes.
It depends on R only. Okay. So that's the first case, simple case, the case where you are static, okay, just a dipole. Now if this dipole start to oscillate, okay, this expression is not true anymore. You introduce the retarded potential, okay, that's what we saw last time. So we have now the same thing but oscillating, okay, so the field is changing with time. So the incident field induces charge oscillation. So this oscillation can be generated by the incident field. Okay, the electromagnetic field is oscillating, so the dipole will also oscillate, and that will induce a current. Okay, which is related to the derivative of P. Okay, so that's another nice representation. Okay, so the oscillating dipole moment produces in turn a radiating field which interferes with the incident field. Okay, so that's always the same story. You have an incident field, it generates an oscillation of the dipoles inside the medium. Okay, this oscillation in turn will generate a field which is actually the scattered field. Okay.
The incident field is the field in the right picture?
So the incident field is responsible for the oscillation of the dipole, okay? Because it's not static. This is the incident field has some
changes at time.
Yeah, it changes with time, so it oscillates with time. So the dipole also will oscillate with time, okay? And this generates actually a correction, which is the retarded potential that we learn and that we are going to describe in more detail here. Okay. So what is the method? You calculate the retarded potential, if you remember from last time. From the retarded potential, you can get the B field and the E field. Okay. The B field is just the rotational of A, and the E field is related to the B field directly with the Maxwell equation. Okay. So that's the Maxwell equation, the Maxwell Ampere equation. In the case when you are single frequency, monochromatic wave. Okay, so let's go. So we have the general expression for the retarded potential. Okay. So that's what I gave you last time. J is the current, the local current, or the density of current. This term is typically the spherical wave retarded. Okay, there is a delay due to the distance r relative to r prime. Okay, so we take into account the speed of light if you want. In the dipole approximation, which means that we are very far, or the scattering is very small, so r is roughly small r. All this simplify, I mean, you can take the exponent and the denominator can take it out of the system, of the integral. Okay, and this integral is just the derivative of p. So that's the expression in that case, in the case of the dipole approximation for the rotated production. That's what we discussed last time. So from this expression of A, you can calculate B. So B is just the rotation of that expression. So the rotational of this product here, again, P depends on R prime. Okay, so you can take it out. So you end up with the gradient of the exponential IKR over R times P. I mean, not times P, vectorial product of P. Next. So what I did next was simply to express the gradient. Okay. So where does it come from? So yes, this yeah, because this is the gradient of a product. This term times 1 over r. Okay, so you have a formula for the gradient of a product. So this term out times this gradient plus the gradient of this term times 1 over r. Okay. So we can group the terms together, and you end up with this expression for B. So only this exponential IKR over R here, and 2 term 1 minus 1 over IKR.
It's funny how it started way more beautiful, like the expression,
Yes.
and we developed it.
Yeah, it becomes more. No, but it's not. This is still tractable.
Yeah, it's very nice.
Okay. At large distance, the first term, so I guess the first term is this term here, and this term in 1 over r dominates, okay? So at long distance, you can ignore this term if you want.
Yes.
That would be like
Close to 0.
So from here, from this expression, we can calculate, we can compute the E field. Okay, the E field is given by the Maxwell equation directly. So okay, you have this different term taken with the rotational of B. So I don't go into the calculus. So now we start to be a little more complicated, okay, a little more involved. But how do we read this equation? You have a first term here, which is the far field term. Okay, that will be the term that will dominate in the far field, because here we have r cubed and r squared. So this is the term that will dominate in the far field. And the other term here is the near field contribution. And the near field contribution actually is directly related to what we calculated before, which is the electrostatic dipole. Okay, if you remember, I should have put it here. Ah, here. Yeah, that's the expression that I put this term on of 1 over r cube. Okay, this is the term here. You recover this term actually. This specific term is the electrostatic dipole, okay, minus the correction. Okay, so far field term, near field term, including the electrostatic dipole and the correction due to the retardation due to the oscillation of the dipole. Okay, so okay, very nice. So at large distance. So wait, before that, so that's the expression for ER. So wait, so we have, if I come back here, we have E of R. Alright, so we have, so this is orthogonal to P and R. and again orthogonal to R. So these two terms actually they are orthogonal to the direction of propagation, right? Yeah, I'm not sure because of this term, the 3 here changes actually the direction here. So if you take only the contribution, so you can decompose the field into on the polar coordinates ER and E gamma. Okay. So you have these two expressions here. So that comes from the previous formula. Okay. You see actually, I think that this term here, I mean, if there was no 3 here, that would be the orthogonal component to the direction of propagation. Because of the 3 here, you introduce in the near field, you introduce a component which is not orthogonal to the direction of propagation. So it gives you these 2 contributions, one in the direction of R, and one which is the gamma, the theta, the angle contribution. So if you are at large distance, you see that E of R, so the component, yes, so the component in the direction of R will be 0 because you are either in R square or R to the power of 3. And the E gamma will give you this component will dominate here, okay, which gives you this expression here in the far field. Okay. Okay, so that tells you actually that the exact solution has a component both orthogonal to R and also in the direction of R, but that's true near the scatterer. Far from the scatterer, this component vanishes, and you end up with only the orthogonal component here. Okay.
Do you want to take a break? No.
Yes, it's good time.
It's now 4 o'clock. 4:02.
Yeah. So let me just click here. So the problem of order. Okay. Just to interpret this equation. So the fact that E of R is vanishes. Okay, this tells you actually that you have a spherical wave with E field and B field perpendicular to K. Okay. If yeah, there is also the other angle in the spherical coordinate. This one is just isotropic. Okay, so we don't consider that, but this is just symmetry of revolution around the dipole direction. Okay. So in this figure here, you have also this angle here. That's the phi. Okay, so you have symmetry of revolution. And E gamma is proportional to 1 over R. Okay, and this is simply for energy conservation purpose. Okay, so the Poynting vector flux through a sphere of radius r squared is conserved thanks to this term here. Okay, so that's the expression that is left in the far field. Okay. Oh, that's also important. So the gamma is just proportional to P. So to the dipole moment of the dipole. Okay. So we can stop here because next, so we started with a static description, okay, simply a dipole. Now we have a dipole which is excited by the incident field, okay, that re-emits, okay, and we are able to calculate the complex, quite complicated expression for the field, but which simplifies in the far field, okay, given by this expression, okay. Next we will go to the green formalism, okay, and we'll see how to use it to describe this question. Okay?
Okay.
So we meet in 10 minutes. That's okay?
little bit earlier because my mom has a birthday and I also have a wedding to attend. Both of them are today. But not too early, like something like an hour from now. Not too bad.
It's okay to-
Maybe half an hour before the time it's supposed to be.
I hope I will be finished with this.
Yes, but if not, so I will read the. I also read the other one, like as you said in the email. So, thank you.
כן,
Okay, so we start. So we went from the static case, okay, no oscillation of the dipole, to the case where the dipole oscillates because of the field is incident field, and we use the retardated potential to calculate. So we are always in this approximation where we are far, okay. The expression of the retarded potential assumes some distance from the scatter, okay. That was the approach using the retarded potential, calculating B field, E field, close, so can be close, but not at the position of the scatter. Now with the grid formalism, we are going to take a big risk, okay, we are going to be inside the scatter and calculate the field inside the scatter, okay? So that's the next step, if you want. That's what we are going to gain here. So again, we are always in this approximation where the scatterer is assumed homogeneous, which means uniform dielectric constant, center at R0, okay, as we said before. So if the dielectric constant is uniform there, so the field is also uniform, so we can write at least this simplification that E of R is equal to E of R0, okay. And okay, the scatterer is placed in the uniform electric field incident. So scatter on field caused by the electric rotation modifies this field both inside and near the scatterer, as we said before. And we have the integral formulation. Okay, E of R is E incident plus the scattered field here, given by G0, the integral over G0. So that's the free space Green function times the polarization, which is given by epsilon minus 1 times the field inside the scatter, okay? So if we assume that the dielectric constant is uniform inside the system, there is an obvious simplification here. If epsilon does not depend on R prime, so we can take this term out of the integral, okay? So that's already something, okay? So we can write it like that. Take epsilon minus 1 outside the integral, and we are left with this expression, which gives you the field at position R as function of the incident field, and here the field inside the scatter. And that's always the problem here, is this quantity, okay? So we are going to take some risk now and calculate the field within the scatterer E of R0, okay? So why is that a problem? Simply because, so if we calculate E of R0 here, we must be careful. Why? Because if you take the limit R prime going to R0, the center of the scatterer, okay?
Singular point?
Yeah, we have a singularity here because you see the expression of the Green function, the Green function in free space is exponential IKR minus R prime over 4 pi R minus R prime, okay? So we have a problem integration over this volume here of the field inside the system, especially when you get close to the singularity at R0. Okay. But if you are careful here, you can see that this problem is only for the real part. The imaginary part we can calculate. Okay. There are different ways to see it. You can simply decompose here the exponential. So the complex exponential. So this is cosine k r minus r prime over r minus r prime plus I sinus I k r minus r prime over r minus r prime. So the sine kr over kr, we know that when you go to 0, this is 1, right? That is called the sinc function. The sinc function doesn't
it's
go.
like a Gaussian, right? It's a peak.
It's peaked. It's peaked at 1,
yes.
and then it oscillates. Okay.
So
That's the sinc
side.
function.
Yes.
So we know that sinus of kr over kr, which is the sinc of kr, is defined at 0. I mean, there is a limit at 0. So the imaginary part has no problem actually. We can calculate it. Okay. It's okay or yeah. Okay. The only problem will be on the real part. Okay. So if I write it like that, I wrote it here because the real part of the free space wave function is singular at R prime. So I can decompose the field at R0. Now I'm inside at R0, okay, at the singularity. So this is the incident field at the singularity plus k squared epsilon minus 1. Then you have the real part and the imaginary part. Okay, so the real part, I keep the integral here over a volume that shrinks toward the singularity. Okay, so the real part of G0 E R prime. Okay, and out of the integral, you can write that the imaginary part is the imaginary part of G0 at R0 omega times E of R0, and delta V is the volume, the volume of the scattering center, which goes to 0. Okay, which is the volume of the scatter itself. Okay, so yeah, nothing to do with this delta V actually. Here you want to do the integration. So the way to do it, so this term is defined, okay, and actually this term gives you 1, so it's a simple term here. This term we are not going to calculate it because I hate this calculation where you take a sphere on the singularity and you make it go to 0, okay. So you get actually the principal value from this integral. Okay, so that's for the imaginary part. This is simply actually this expression. Imaginary of G0 is given by the identity times some factor. Okay, but the real part can be calculated for a volume delta V that goes to 0 here, and is equal to E of R0 over 3k squared minus E of R0 over 3k squared. Okay, so it simplifies nicely after some calculation. Okay, I'm not giving you the troubles here.
So you used Cauchy to calculate the imaginary.
Yes, exactly. Okay. Okay, so if you take this, you replace this in that equation here, so you have E of R0 on this side, the incident field on this side, and you have here E of R0 also, and the last term also is E of R0, so you can group and you can express E at position R0 as a function of the incident field. Okay, so for instance, you see that you have here k squared epsilon minus 1 times this term. So the k squared is eliminated. So you have epsilon minus 1 over 3. Okay. So this contribution, you bring it here. So you have there is a minus. So this 1 plus epsilon minus 1 over 3, which gives you epsilon plus 2 over 3. Okay. that's the term that you see here. You have epsilon, so it's you take the inverse. You have to invert it. So you have 3 over epsilon plus 2 here, okay, times the rest. So the rest comes from this term, from the imaginary part, okay, and is given by 1 minus I3 delta V, the volume of the scatterer, K3 over 6 pi, epsilon minus 1 over epsilon plus 2, okay, 1 over. So that's the formula. Now we have a formula that gives you the field at the singularity inside the scatterer, okay, as a function of the incident field at the same position. Okay, so that's nice. We can give some interpretation here. For instance, the first term, if you look at the first term, so in the limit where omega goes to 0, the case of the electrostatic case, okay, so this term goes to 0 here, so this one here, and you find that the field inside the scatterer is 3 over epsilon plus 2 times the field, the incident field, and this is well known in electrostatic. When you have a sphere, okay, traversed by a field, okay, you have a field inside which is given by this expression here, okay, due to the charge that accumulates there. Now the second term here, very important. So the second term will be a correction due to the radiation of the scatterer. Okay, so this is the electrostatic case, the static case. Okay, but because the scatterer oscillates, it gives you a correction here. This is the term that we have here. Okay, so it's a dynamic correction. Which take into account that at optical frequency, the frequency of the incident wave, you cannot neglect the fact that the dipole radiates. Okay, so that's the radiative term that you have to add. So you see, actually, it's kind of lost term. Okay, so the field inside the scatterer will be that field here in that static case minus. I mean, there is a term which is due to the fact that part of the energy leaks out, it is scattered out from the scatterer. Okay, so that's a simple interpretation of this equation that we have here. So it's a loss of energy from the dipole due to the radiation, to the oscillation. So from here, from this expression here of E, then we can calculate the polarization. Okay, that's important. Okay, so now that we know the field inside, we know what is the polarization as resulting from the field, from the incident field. Okay, so P is integral here, integral of epsilon minus 1, E of R0 D3 R prime. Okay, this term is constant, doesn't depend on R. This does not depend on R. So just integrate over the volume of the scatterer. Okay, and so if you replace by E of R0 that we just calculated, so that you get this expression for P. Okay, so this constant term here times the volume of the scatterer minus these two terms, so the static term and the oscillatory term, the radiating term, times the incident field. Okay, so that's very nice. This expression tells you I have an incident wave. This is the polarization that I generate inside my medium. Okay, my medium is polarized with this amplitude here. Okay, part is due to the static component, and the other one is due to the radiation out, which is the loss from the. Okay. So a special case, if you have a spherical scatter, then you can take delta V is for third pi R. Okay.
So the second term is a perturbation.
It's a perturbation, but it's necessary. You cannot ignore it. Okay. Yes. I'm going to show you why. But you have to take into account the fact that there is a loss. Okay. Actually, you will see next that this loss, which is the radiation, okay, is responsible for the radiation. Otherwise, you don't have any scattered field. Okay. So actually, you cannot ignore it.
Like dumping.
So from here, we can calculate what is called the polarizability of the medium. Okay. So the polarizability is defined as alpha here, which relates P and E incident. Okay. So this alpha contains all these complicated terms here. Okay. So this is a physical quantity, the polarizability of the medium. Okay, alpha. So that gives you some expression here. Okay. So I can factorize alpha 0 here. So alpha 0 will be what is called the alpha 0 okay. Yes, I mean the dependence with omega is not due to the fact that there is an oscillation. Alpha 0 is the quasi-static polarizability, okay? Okay, so that's really the term for the case of the static field. There is no oscillation, no retarded potential in that case, okay? This is given by this expression. This is a well-known expression for alpha 0. Okay, and that gives you typically how the medium, what is the amplitude of the polarization of the medium due to a given incident field. Okay. That's really the first term here. What is the difference between alpha 0 and alpha? It is this term here. Okay, so this term. This term actually represents the dynamic part, okay? The fact that you have an oscillatory field and an oscillatory dipole. So the scatterer will radiate. So there is a radiative correction, as I wrote it here, radiative correction. Most of the time, alpha is approximated by alpha 0, okay? But you have to be careful because this term is necessary to conserve energy. Okay, if you remove this term, you lose conservation of energy. Okay, so we see how it occurs in cross section. So you remember cross section? Yes. Okay, so that's what we said. The scattering process induces a dipolar moment. The power radiated by this dipole moment is equal to the power scattered by the scatterer, okay, and is given by this expression here. That's from last course, okay. But now what is new from last time is that now we have P, okay. We have an expression for P because we know what happened inside the scatterer. So we defined last time the cross section. By definition, the power scattered by the scatterer is equal to the incident intensity falling on the scattering cross section. Okay, so the intensity incident on this cross section gives you the power which is radiated by the scatterer. Okay, and is given by this is just by definition. This intensity here is given by E squared with some constant in front of it. So you can replace that and you can calculate the sigma from this expression. We have everything, we have that and we have that now. So you can calculate sigma and you find that the scattering cross section is given by k to the power 4.6 pi times alpha 0 of omega squared. Okay. So you see that sigma is proportional to omega to the power 4. This is the relay scattering. I mentioned that also last time. Also, sigma depends on, if it's a sphere, so it depends to the radius to the power 6. Okay, so that's important actually. The dependence on the radius is alpha 0 is alpha 0 equal to volume. So So it's R6, right? So there is, you have to be careful. I mean, even if the wavelength is small, even if omega is small, it also depends on the size, 2 power 6, the size of the scatter. So it has to be a small scatter compared to the wavelength. Okay, so that's typically the Rayleigh scattering. We remember this plot that gives you the how did we call the cube? So that's the ratio between the cross section and the physical cross section and the geometric cross section. Oh, the scattering efficiency. Okay, that's the name. Okay, so it tells you that at small frequency, so large wavelength. Okay, so x equal Ka. So for small omega. Small frequency means large wavelength. Okay. So for large wavelength, the sigma is small. Okay, and then it increases with frequency. So you see here that if you shine light on this translucent object, you see the blue is scattered, and then the yellow, then the red. Okay. So the blue which corresponds actually to a small wavelength. Okay, so we are somewhere here.
Large frequency and a small.
Yeah, so that means that
wavelength.
the first thing to be scattered is the blue. Okay, as we show it here also. Okay, so that's the idea that you have the sun at sunrise or sunset actually cross the atmosphere. Okay, so the blue is first scattered, and then the yellow, then the red. So you see the red sky. Okay. So I think we have done most of the story, the hard part. Okay. So I try to show you that actually we can calculate almost everything, but for simple cases. Okay, so starting from the integral formulation using the Green's function, you can calculate in the case of small scatter, you can calculate the field inside, which is really the problem in this integral formulation. You can calculate the field inside the scatterer. Okay, and from that you can recover actually all the elements. So now we have all the pieces of the puzzle, if you want. Okay, now we know how the incident field modify the medium, how it polarizes the medium. Okay, what is the field resulting from this polarization in the near field and in the far field, inside and outside the medium. Okay, so we have all the chain of the scattering process now, and we have some tools to handle that. Okay, so if you remember at the very beginning, I mean, we discussed the scattering amplitude of the scattering matrix. So you have an incident wave, you have a scatterer, and in the far field you can observe in a given direction. Okay. If you have also polarization can be also changed during the scattering process. So what happens in the case of the Rayleigh scattering? Okay, so that's something that we did last time. Dipolar approximation. We have the expression for A of R. Okay, from A we can calculate the E field. That's from last time. The field scattered in direction U is the field radiated by the dipole P in the far field. Okay, so we have here the expression for the scattered field that we calculate today. Okay, so that's actually the scattered field. So this is using P. Where is it? Where is P? Oh, here. Here. So we replace A. So I omega A orthogonal from this expression. So you have mu0 over 4 pi exponential IK. This comes from here. The P, the polarization gives you this term here. Some epsilon disappears somewhere, okay? And this is by definition that we gave the first time, the first class, the second class. That gives you, this is given by the scattering amplitude here, S of u, times the spherical wave experience IK. Okay, so now we have actually an expression for S of u from this equation here. Okay, so today we calculated that, and last time we put it in this form, and now we have a way to calculate S of u. So for the case where there is no depolarization, for instance where the scattering is spherical, then you can project onto the parallel direction, parallel to the plane and orthogonal to the plane of scattering for the scattered field and the incident field. And you obtain a scattering matrix, which is given by this expression here. Okay, so this is the expression for the case, the particular case of the Rayleigh scattering. Okay, so you see that there is no cross term. You don't cross polarization. The polarization is maintained. Okay, and you have one in one direction and cosine theta in that direction. So if I represent these two terms, so if I project that onto one direction or the other direction, okay, I have two diagrams, two different scattering diagrams. So you see them here. So this is the direction of the polarization, okay. Polarization is, so if I'm coming here with the polarization parallel to the dipole, okay, the dipole will re-emit with these two lobes. That's the cosine theta, okay. So that's the emission when you come that direction. And if the polarization now is perpendicular to the plane like that, okay, so you come with the plane wave and you have a radiation field which is circular like that, okay. So if you combine the two, don't forget that we have also the phi term, which has a symmetry of revolution. So actually, the scattering by a small particle looks like this donut shape. Do you see it?
It's between.
Yeah, the donut. Okay.
It's like the electromagnetic fields in a solenoid, no? No.
Yes, but
it doesn't like.
I don't see the connection with that.
Yes, no connection with that. So
Same
mine
shape.
is milk. Yes.
So this is basically a coffee mug.
A what?
A coffee mug.
Yes. So that's Rayleigh scattering. So for two different polarization, most of the time light is not polarized. I mean, it's a mixture of polarization. Okay. So when it's a mixed polarization, and you mix the two components, and you can write it like that. It's called natural light. For natural light, you have both components that are scattered. So the intensity which is scattered is given by this expression. This is the two terms actually, 1 plus cosine squared. So that gives you such a diagram for unpolarized light. Okay. The number, check the number are very small here. Okay, so the scattering is very small. It's a small particle. Okay. But we'll see what happens when you have many of these small particles. What happens with multiple scattering? Okay, so you remember that we defined the extension, cross section. So what did I write here? Yes. Oh yes. Okay. So that's the optical theorem. You remember the optical theorem? You look in the direction of incidence. You look at the light that is scattered in the incident direction, in the forward direction. Okay, so the scattered in the incident, the forward direction is given by this term here. Okay. Optical theorem tells you that the extension cross section is 4 pi over k, imaginary part of S0 or SU incident, the same. Okay. So you see that to have an imaginary part here, you need to have alpha complex, right? If you take alpha is equal to alpha 0 is real, so you completely miss actually the radiated field, and you don't have any scattering from the object. Okay? So by conservation of energy, or by the fact that part of the energy is lost by scattering, okay, you need to take into account the correction on alpha 0 in the expression of alpha. So that's another way to see the importance of this extra term due to the retardation, to the oscillation of the scattering. Okay. Over all these formulas, I really want you to keep the idea, the physics behind that. Okay. So here the radiative correction that we have for alpha gives you the imaginary term of alpha, which is needed here. Okay. Actually, I put it here just to remember. Okay. Okay, let's keep that the same. Okay, so we are going to miss the easy part. Okay, let's be like more general now. So now that we know how one scatterer works, what about large scatterers? Okay, a complex system like a cloud made of many droplets of water. Okay, so the first idea is to say, okay, I know what to do in one scatterer, then I can go to 2 and then to n. Okay, so you can build actually your medium starting from the building block that we described before. Okay, just what you have to take into account is that if you have like 2 scatterers like that, okay, in a given direction, you have to take into account also the interference between the fields. So this scatterer will generate a field at some distance, this one also, okay, but because there is a difference of path between the 2 directions, there will be an extra phase term between the 2 fields, okay? That's the general idea. That's for 2 scatterers, and then if you have like an ensemble of scatterers, then you have to take into account all the phase differences between all pairs of scatterers inside the system. So that starts to be complicated. Okay, so you need some way to have some approximation. So one approximation is the case of the Rayleigh-Ganz divided. It's the same, Rayleigh limit or Ganz approximation, divided approximation, which is mostly to say that the index contrast is small. Okay, so m minus 1, m is n1 over n0 if you remember. So the index contrast is close to 1. That the size of scatterer is small compared to the wavelength inside the medium. Okay, and that the scattering is actually weak. And in that case, you can write from what we learned before. You can write the intensity which is scattered by the object here. Okay, so you can this is a way to homogenize the medium. Okay, so instead of considering each element as a scatterer, you consider the ensemble as a big scatterer, but with this condition here where we have weak scattering. And just fly over the different cases. So shall we finish? Or we finish and we go break later. So what about very large scatterers? So very large scatterers means that will be in geometric optic. Okay, geometrical optic. That means that the beam which just bounces inside the object. Okay, so this is the limit of geometrical optics. Reflection, all that. Okay, but it's not only the case. If you remember what we discussed last time, is that it's not simply geometric. Okay, if it was simply geometric, then the cross section, the scattering cross section, should be equal to to the geometric cross-section, right? If it was just a bouncing ball, okay, it will be a, but still we have interference effect, okay? So there is something called the extinction paradox. By the way, one of the papers discussed this topic, one of the papers that I will propose to you for the exam. So the extension paradox tells you that actually if the scatterer is large compared to the wavelength, the scattering cross-section is twice its geometrical cross-section. So Q can be 2. In the limit of large scatterer, Q is equal to 2. Okay? So the object scatter twice its geometrical cross-section. So there is a way to demonstrate that, and this is based on the Babinet. Do you know Babinet principle? Tell you something. Babinet principle. So how do you solve this question? So how can a large scatterer remove more energy from an incident beam than its geometrical intercept? Okay, then what is blocked geometrically? And a way to solve this question is to use the Babinet principle. Okay. No, yeah, you've not familiar, you never heard about that. So the Babinet principle tells you that if you imagine the incident wave. Okay. The incident wave is the sum of two components. So one is, so let's say you have you put a screen with a hole. Okay. So part of the light that goes through the hole here is a component of the incident wave, and if you take the reverse of this image, okay, so an obstacle, a black circular obstacle like that, the rest will add with this part to form the incident wave. Okay, so actually you can see the scattering by an object as being made by two components. One is a component due to the wave which is intercepted by the object. Okay. And the other component is the wave which is not intercepted by the object, this part here, okay? And this part also contributes to the scattering, okay? So to the efficiency Q factor, okay? So that's a simple way to see that actually you double the contribution due to this principle, this superposition principle. You can superpose, actually, you can see the incident wave as a superposition of these two components here. Okay. Actually, this is not true. I mean, this demonstration is discussed. It's not correct. So I invite you. So one of you, I hope, will take this paper. Yeah, can take it. That discuss actually the problem with this approach. Okay. So that's the paper, by the way. Okay, then you can really treat the problem in the most complex sense. But usually the treatment is numerical. Okay, so that is what is called meteory. Okay. So for a general scatterer, okay, you need to solve the Maxwell equation with boundary condition at the interface of the scatterer. So you have a scattering object here. Okay, you have an incident plane wave E0, H0. So you need to solve the equation here of the wave coming, interacting with the internal waves here, IHI, and to get the scattered field here. Okay. So that can be done numerically. It is solved numerically for simple cases, typically the sphere. Okay, and that's, you remember I gave you an address with a simulator that gives you this type of diagram here. Okay, so this is the general case. In general, for a spherical, you can solve the spherical scatterer or the cylindrical scatterer. That's what you can solve numerically with the Mie for the Mie scattering case. So that means that I don't have any more condition on M or on the size of the scatterer. I can treat any size, any index contrast. The only assumption is that we have a spherical or cylindrical scatterer, and it's a numerical solution. I mean, you cannot solve the problem analytically. Okay.
And the phi angle is isotropic. The phi.
Yeah, yeah. You have the phi in the other direction, which remains.
So it goes like that.
So this diagram actually you have to rotate like that. So it's like I show you this picture last time.
Yeah, I remember.
But this, I mean, here you treat the full problem. I mean, this is really the Maxwell equation with the field outside, inside. I mean, all the problem is fully considered, and then you can play on the parameters. So, for instance, I changed. So this is the linear. This is the log representation. So I go from x equal 2 here to x equal 5. So the scattering is more and more in the forward direction. We saw that already. This is 10. Okay. So there is no limit from this point of view. What is interesting is that if you look at the Q factor here, the scattering efficiency factor, you see that. So here you recognize here the Rayleigh regime. Okay, that's the omega to the power 4. Okay, the Rayleigh regime here. But we are very far from that regime. When you get far from that regime, then you have some kind of resonant effect. Okay, there are actually multiple resonances. So there is first this peak, the second peak here. All these resonances correspond actually to what is called whispering gallery mode. Okay, that's actually when you have the wave that bounces inside the sphere. Okay, and I mean you can, due to total internal refraction, actually you can obtain high resonances, and that's why you see these peaks with value very high. You see Q scattering can be very high around the mere resonances. There are also sub-resonances inside. So it's, but this is accurate. I mean, this is something you can use to describe the scattering by one particle.
This shows conservation of energy.
Why do you say that?
Because of the damping.
No, there is no damping here.
Because it looks like
Right. No. So the point is that you remember what I said before?
Yeah.
In the limit of very large scatterer, Q should go to 2. Okay.
Yeah.
So what you see is that if you go to very large scatterer, you go actually you converge to this value 2. Okay.
Yeah.
But before that, okay, even for large value of x here, parameter x, you can be much higher than 2. Okay. And this is because of resonant effect. Okay, you have to realize that actually the light is trapped inside the scatterer. Okay, and that gives you like in Fabry-Perot, it gives you a resonance with very strong peaks.
Yeah.
Okay, so if you want to enhance the scattering, you have to work with mis-scatterers like that, which have this type of resonances. And if all the scatterers they have the same size, you will have like a collective effect. And these are typically the regime where you can reach Anderson localization, you remember, where actually the wave can be trapped in the system because you take advantage of these very strong resonances inside the system. Okay?
It looks like a power law. A power law.
Where do you see power law? I mean the decay.
Yeah, the decay.
That's possible. You can see here. Yes, this is when if you vary, so you keep actually x, but you vary n, the index contrast. So for weak index contrast, you have only this single oscillation. When you increase n, you have additional oscillation inside the resonances. Okay, so that's something that you can treat. Actually. I mean, we have the equation. Actually, you can write the solution, okay, but you cannot solve them analytically. You have to solve them numerically. you can, I mean, these actually the solution are in terms of spherical harmonics, and it's quite this is quite easy to program actually, but you need to solve them numerically. Now you can go to problem where you don't even know what are the solutions. Okay, so the only way to do that is to do simulations. Okay, so this is the case for anisotropic scatterers. Okay, the anisotropic scatterers means that the scattering will depend on polarization. Okay. So what type of anisotropic medium we can have? For instance, optical anisotropy can be found in birefringent material. Okay, you see here. So this is calcite. Okay, you see that when you turn I think it's a polarizer that is turned in front of the calcite, and behind the calcite is written the name. Okay, you see that it moves. Okay, because it depends on polarization. So the refractive index depends on the polarization. You have the case of the uniaxial birefringence. Okay, I won't go too much into data. So you have uniaxial and birefringence. Okay, so depending on the orientation, you may have one direction with large index of refraction, in another direction with lower index of refraction, and this gives you actually, dependent on the polarization, this gives you different behavior in terms of refraction. So let's say we have a scatterer made of this material. Okay, another type of material which is birefringent is liquid crystal. Liquid crystal is strongly birefringent, depending on the polarization. So that's the case here. Liquid crystal. They are made of molecules which are elongated like that. Okay, represented by this kind of elongated molecules here. Okay. So usually you have different phases for this type of system. You can have either the solid phase where everything is ordered, aligned. You have the liquid phase where everything is random, and in between you have the liquid crystal phase, which has some degree of order. Okay, and this is called the nematic phase. That's a specific case of liquid crystal. And what is nice is that this molecule can be actually oriented. Okay, you can apply the field and you can orient more or less these molecules. So we can go from a disordered system to a more ordered structure. Okay, and you can have some birefringence effect that you see here behind the polarizer. So we have done in the past, a long time ago, we have done some experiments where we have considered liquid crystal in small spheres. Okay, so it's like a scatterer filled with liquid crystal, so it's completely anisotropic in terms of scattering. Okay, and it's a very interesting device. Actually, this is a device that is used today. So it's called polymer dispersed liquid crystal. Polymer PDLC. So this is a typical case. So you have these kind of spheres made of liquid crystal. Okay, embedded in some polymer. So these like in a gel or in plastic. Okay, they are randomly distributed in the system. Okay, but if you apply the field, static field between two electrodes, the liquid crystal inside the scatter will align with the field, and then you can have everyone align like that. Okay, so if you are smart enough, you can make it transparent when they are aligned. Okay, if let's say the index of refraction for some given polarization is the same as the index of refraction of the matrix here, the polymer matrix, then you can have a medium which is transparent. Okay, and when you release the E field, the medium becomes scattering. Okay, So you can switch the system from transparent to opaque, okay, with an electric field. Okay, so you see here demonstration here. So no electric field, so you see actually you can see optically these droplets of liquid crystal, and as you increase the field, you make the system transparent. And that has been commercialized to make windows that you can switch from transparent to opaque.
Small glass.
Yeah, exactly. Yeah. So that's something that is used. So at that time we wanted, that was really the starting of this business, and we wanted to model actually the scattering by one of these objects like that. Okay, but it's complicated. It's a scatterer which has a scattering which depends on polarization. Okay,
but in reality, the scatterers in the glass, like for example, they are not like I don't know, like here where you have like a spherical shape. So then, is there any like influence of the direction of the pointing or something like that?
You mean of the polarization? In that case, it depends on the polarization.
Ah, okay. Change the polarization.
I show you the simulation. Okay? So
Okay,
we have done simulation where we simulate the Maxwell equation, the full Maxwell equation. Okay, it's two-dimensional. Okay, because it's easier to take less time to compute. And we start with, we have a scatterer here, okay, which has some direction of birefringence, okay. So depending on the orientation of the scatterer, you have a plane wave incident on this object, okay. If you choose the index of refraction for one given direction to be the same as the background, okay, you have actually a system which is transparent in that case. When you rotate by 90 degrees, you have scattering effect. So you see actually the scatterer, you see the field inside the scatterer, okay, and you see the field which is radiated away. So you see that it's the sum of the incident field and the radiated field, okay. We are still in the near field here, but if you go further away, you will see and if you orient completely randomly, I mean, if it's a random orientation of like 45 degrees here, then you can have a diagram of a scattering diagram, which can be very strange, very specific, right? Okay. So that's the numerical simulation, and then you can go from one scatterer to many scatterers. Okay. So that's what we have done here for like a slab of these liquid crystal scatterers. And you see that if they are oriented all along the same direction, polarization, then the system is completely transparent. And if they are randomly distributed, then the system becomes scattering with a very complex scattering scheme. Okay.
So in smart glass, we waste energy or electricity just to make it transparent. Because
right, so that's not a good solution.
yes.
Yeah, because if you have like failure in power, then everything will be opaque, right?
Mm.
So they have been working at that time to do the reverse, the inverse of this system, which is a system without field it should be transparent, and with field it becomes random. And what we have done, the research we have done in this system is so it goes a step further, which is so instead of applying a field that orients the scatterer like that, the electric field of the incident wave can also interact with the scatterer if it is strong enough, so you can have a nonlinear effect. And in liquid crystal, the nonlinear effects are huge. I mean, they are like very, very strong. And the electric field of the incident field can reorient, can modify the orientation of the liquid crystal inside each scatterer. So you have a wave that comes, okay, and because it is intense, it will change the orientation of the scatterer. Light will be scattered in another direction. The scattered light will change the scattering of the next the next object. Okay, so that's a complicated effect of what is called nonlinear scattering, where the medium, the scattering of the medium changes with the incident field itself. Okay, and the idea was to use that to design what is called an optical limiter. You want, let's say, you want to protect your eyes from a laser light. Okay, so you want to wear glasses like that, where the system is transparent. Okay, at low intensity. But if you get like a high an energetic pulse from a laser, the laser will orient randomly the scatterers, okay, and the system by scattering will reduce the light to diffuse light that can be stand by the eye. So that was the idea to make actually this type of optical limiters of glasses that protect from radiation, from strong radiation, like for pilots, for instance. So that was. So that's it. I wanted to go all the way through to the most complicated case. Okay. And with that, I thank you with the signature of George Latour. Any question? I didn't stop, but I hope.
Thank you.
Thank you.
Okay. So next time we'll take now we have this building this toolbox, okay, with this building block that we can use now to build the multiple scattering. Okay, we'll try to see how far we can go with that based on the board approximation and successive term. Okay. Thank you. See you next week. I hope it was not too heavy.
The beginning was there was this paper you talked about last time.